today, I have kind of three places I want to go today, just so you guys know, and a bit of a trip. We are talking about net force equals MA, but translating it into net torque equals I alpha. That's what's happening. We're moving from translational motion to rotational motion. So we're talking about Newton's second law. This is dynamics. We did statics questions last week, questions in which the net torque or the net force equals zero. But dynamics questions assume an unbalanced torque, and therefore the system's going to begin to rotate. What you have to know for the AP1 curriculum is pretty pedestrian. And what I mean by that is it's not very deep. They just want you to kind of have an exposure to the material. However, I say that knowing last year they asked a pretty deep question on the exam that required quite a bit of knowledge. So what I want to do first, before we go into any of this, is remind you of a couple little things that I think you will remember. First, work equals the change in kinetic energy. I believe you remember that. Now, it's not that simple. It's net work equals the change in kinetic energy. Or there has to be work done by an unbalanced force, but that's what we're talking about today is unbalanced forces. So I think I'm okay just saying net work. So there's got to be an analogy here. Something where the net work can change the kinetic energy. So, and there is, work can be done to change the rotational kinetic energy. Now, I don't want to prove this to you, and I could, but I don't want to. If kinetic energy is 1/2 mv squared, bless you, can you imagine what rotational kinetic energy probably looks like? You've seen, I hope, a lot of similarities. So instead of having inertia as m, what do you think inertia will be for rotational kinetic energy? What's that? Yeah, so what symbol? And we're not going to talk about linear velocity. We're going to talk about angular velocity. So what symbol is that? Yeah. That shouldn't be a big deal, a big surprise. That if there's a rotational kinetic energy, it would look like that. Now, to understand rotational kinetic energy, just be aware, the object's not changing location. The object's spinning. But if you have a disk that's spinning about its middle, like so, even though this object might not be going from one place to another, a piece of mass, some little piece of it right here, isn't that thing moving? As long as any part of an object's moving, it must have kinetic energy. This represents the kinetic energy of all the individual pieces as they're spinning around some axis point. And it takes into account the fact that a piece right here is traveling faster than, say, a piece right here. It already takes that into account. So it is a great way of understanding that the kinetic energy is based on the moment of inertia, which knows how the mass is distributed, times how fast it's spinning squared. It's an energy too, just so you guys know. It works just like all other energy, meaning that it's in joules. It obeys conservation of energy. And most importantly, objects can have two kinds of kinetic energy. They can have translational and rotational. So, and this, I'll go a little slow because this can get to be kind of hard. All right, so If I say that this ramp is frictionless, and let's just say that the ramp looks something like that. So the box started at a height up there and is sliding down the ramp, accumulating kinetic energy. If you think back to first semester, the box at the top had energy mgh, and when it makes it to the bottom, it's going to have kinetic energy 1/2 mv squared. Do you guys remember that? No big deal, right? Okay. Now, would you agree that if there was friction there, the box would make it down, probably traveling slower? Does that make sense? Okay. Will it have more energy or less energy when it makes it to the bottom?
Less.
Where did the energy go? Friction. That's right. Probably heated up the two surfaces or something, but work was done by friction, which took energy away from the box and left it spread out all over the ramp. Remember those conversations last year? I hope so. It'll make what I'm about to talk about a little bit easier, because let's get rid of the box for a minute and consider something that is round. Now, this part's going to be hard, I promise. So if you're going to pay attention at all today, don't blow off what I'm about to talk about. If we assume it's frictionless, and let's say this round thing had the same mass as the box, it still would have started out with mgh up here. But if the ramp is frictionless, that will still be 1/2 mv squared here, because without friction, the ball slides down the ramp. The only way you can get something to turn is if there's an unbalanced torque acting on it. With no friction here, it just slides. So there's no difference between a block sliding down a frictionless ramp and a ball sliding down a frictionless ramp. You guys who are really, really intuitive, you understand we're building the multiple choice question as we're talking, right? Because we're going to live inside these little details about whether there's a little friction on the ramp, whether there's no friction on the ramp, whether the box and the ball are the same size or different sizes. Those are the details you miss in these questions. So I just gave you one. I gave you the answer to one. A box and a ball that are the same mass will behave the same if there's no friction. However, the box, when it experiences friction, has less energy when it makes it to the bottom. A ball that experiences friction, that's a little different. The ball that experiences friction won't slide. What will it do instead? It's going to roll. Now, listen carefully to what this means. If the ball rolls, when it makes it to the bottom, it will have two kinds of kinetic energy. It'll have 1/2 mv squared because the middle of the box is moving. Right? When it makes it down there, it's going to clearly have a velocity in that direction. But it's also going to have an angular velocity, so it will have 1/2 I omega squared. Now look, there's a finite amount of energy, mgh, at the top that now has to be spread out into two different types of kinetic energy when it makes it down here. So, when something rolls, it's going to have a lower velocity when it makes it to the bottom, because the energy has to be divided up now. Some of it's translational, some of it's rotational, so together it's going to be slower. But it doesn't lose any energy. None of the energy is lost to the system. It retains all the energy. The box that slides down the ramp experiencing friction loses energy. It leaves the energy on the ramp. But in this case, the friction causes a torque and just converts some energy from translational into rotational. Now, this is the kicker. This is the hard part. You already know the answer to this. But which object will be rolling faster at the bottom of the ramp? The disc or the ring? The disc is easier to turn, so it makes it to the bottom faster. Easier to turn. If I is small, it will have less rotational energy. If I is big, it will have more rotational energy. But there's only so much energy available. So when I is big, this is going to take up more of the energy than it would if I is small. We already know, and this part is where it gets complicated, but we already know that these two things are going to be related. They have to be. V equals omega times r. So its linear velocity and its angular velocity are linked together. But this explains why the disk makes it down there first. This explains why the ring is slower. The ring is harder to turn. So as it rolls down the ramp, it takes away more of the energy in the form of rotational kinetic energy, because it's harder to turn. Now, we're not going to really do much about the math of this. I need you to have an appreciation of this. The math of this has a lot of algebra in it. It's not terrible. It's just outside our scope. So we need a qualitative understanding. You need to be able to predict what types of objects will roll faster and what types of objects will roll slower. You need to have an understanding that we still have conservation of energy. Okay? So for the next few minutes, we're going to talk about what it takes to get something to spin and use Newton's second law to do so. So I want to talk about the meter stick lab for just a minute. One of the things that you might have noticed is that a lot of people found that their meter stick kind of collapsed once or twice, and they were trying to get it to carefully balance. In that they thought it was going to balance, they let go, and the whole thing went kaput. That's because they probably hung something that they shouldn't have and caused a torque that got the system to rotate. So if you hang something here, you are applying a torque to the system. Let's assume that we have a balanced meter stick. And exactly that, it is a meter stick. So how long is the meter stick? A meter, thank you. And you guys all measured the mass of your meter stick. What mass did you get? They're all about the same. Do you remember?
Around 93.
I'm using that because the moment of inertia of a meter stick is 1/12 ml squared when pivoting about the center. Remember, we talked about moments of inertia on Friday. This is the moment of inertia about the center of the meter stick. We're going to hang a 50-gram mass off the edge. If that's all we hang, will the system stay still? No. It's going to rotate. Is it going to rotate clockwise or counterclockwise based on what I've drawn? So, we are going to have a clockwise acceleration because there's an unbalanced clockwise torque. You hear all that language? That's the kind of language you're going to need to be able to write on your test. Qualitative discussion. This system will have a clockwise acceleration because of an unbalanced clockwise torque. They want you to use clockwise, they want you to use torque, acceleration, all of it needs to be there. Let's assemble this question. This question is, what I would like to find for this question, by the way, is I would like to know what is the angular acceleration of this system. This is an F equals ma question. To do this problem, you have to recognize three things. First, you have to compute the one unbalanced torque, because there's only one unbalanced torque, which means starting our problem realizing that the torque has three components. There's the torque arm length, there's the force applied, and then there's the sine of the angle. All three pieces. If we place the 50-gram mass at the end, what is our torque arm length? Let's do it all in meters and kilograms. So 0.5 meters good for all of you? Excellent. Now the force applied is the weight that was put at the end. That's going to be mg. Well, the m in this case is 0.05 kilograms. And g is 10. And lastly, assuming it was started level, it'll be the sine of 90 degrees. Any question about what I put there? All of this represents the torque. Remember, force was easy. It was usually much faster. Torque has all these different pieces. So 0.5 times 0.5 is 0.25 meter newtons. And you're all taking out your calculators, and I'm glad, but I want this to be less about you having to push buttons and more about us being able to focus and seeing how this works. So this is the one unbalanced torque. Next, this object's inertia is based on rotational inertia. So that's over here. 1/12 m mass of the meter stick, 0.1. This is not the mass that's hung. This is the mass of the meter stick. L squared, 1 squared. Good so far? Feels like we're pretty close to being done, doesn't it? We could just take this and put it here for torque, and this and put it here for I, and it feels like we would be done. Any question about what we're going to do next? I'm sorry to say that that's not it. In real physics, we would have to take into account the moment of inertia of the mass. Right? If you hung it on the end, wouldn't it also accelerate? That would make this really hard. We're going to ignore that for this instance and assume that somebody's just pulling on it with this force. But remember, anything that moves has inertia. If the mass were going to move, we'd have to include it. But for this example question, I want to kind of make it more straightforward. So we'll ignore it. We can now assemble our problem. Net torque equals I alpha. So 0.25 equals 12 times 0.1 times 1 squared is 0.1 divided by 12. I have a reason to do it this way. It's not a great reason. It's just laying it out for us. If we want our answer, we just solve for alpha, which will be 12 divided by 0.1 times 2.5. I'm sorry, not 2.5, 0.25. Thank you for not correcting me. I didn't want to be corrected today. There. I'm pretty sure this is 30 radians per second squared. Pretty sure. I mean, you can check and all, but I've been wrong in the past. In fact, I might be wrong, but I don't think I am. Am I good? I know some of you are pushing buttons.
Yes.
Now, do you understand first that net torque equals I alpha is just Newton's law again, but every part of it requires a little more work than what we did before. We can't just put in the mass, we have to find the moment of inertia. We can't just put it in the force, we have to figure out what the torque is. And then once all that's assembled, we can use it to figure out alpha. Okay so far? It's going to get a little harder. Do you want maybe a one about this level first as practice? All right. Now, just so you guys know, there's only like, at this point, less than half of you actually paying attention. You guys who are not paying attention, you're easy to spot. I would encourage you to recognize we're going to go fast on this. If you're not paying attention, tomorrow, if I decide I want to see what you're able to do, you might be in a world of hurt. I'm going to hang a meter stick with a string on both ends. Okay? Same meter stick. We'll assume the center of mass of the meter stick's at its middle. I am going to cut the wire on one side. I'd like to know what the acceleration is of the meter stick right when I cut the one string. I'll say it again, because getting the words of this sample problem into your work is probably useful. I'm hanging a meter stick from both sides. I am going to cut one of the strings. I'd like to know the acceleration of the meter stick right after I cut the string. These accelerations only last for an instant because once the system starts to move, the angles start to change right away. So they always ask these questions like this, like what happened right at the very beginning. So what we actually will have is this situation. The weight of the meter stick is going to cause a torque on the meter stick. But since there's a pivot point here, the meter stick doesn't fall to the ground, it rotates about the pivot point. So we want to figure out what is the acceleration based on that one unbalanced torque. Okay? Tough question. Tough question. Let's say the meter stick is still, what's the mass of the meter stick? 100 grams, yep. We're going to need the moment of inertia of a meter stick about its end, not its center, which I know you guys have in your notes from last week Friday, those of you who took notes. And you'll be able to tell me exactly what it is. 1/3 ml squared. So I know it was written on the board. I wrote it. It's still there when I got here on this morning. So just like before, we have to assemble this problem. We're going to have the torque on one side, R, F, sine theta. On the other side, we're going to have the moment of inertia, 1/3 m L squared, and then alpha. Now, my assumption is that we've seen a couple of these. I don't want to belabor it. This is not going to be that big of a part of our test, but these two are pretty easy examples. Tomorrow, we're going to look at one or two easy examples and then a couple of hard examples. From there, again, saying that the length is 1 meter. What is going on? There. Length is 1 meter. What we have to do next is not too bad. The torque side is the side that we tend to struggle on for something like this. But if you remember, the whole idea here is that I have one side tied, by a string. The other side was, but I cut the string. So the whole thing is going to do that. Would you agree with that statement? All right. So actually doing the calculation is not hard. We do the torque on one side, and we put I omega, we do I alpha on the other side. So the torque is going to be whatever this torque arm length is. What do you think that torque arm length is going to be? 25? 0.5. I'd go with 0.5. Sure, 0.5 meters. The distance to the middle of the meter stick. That's where the gravity is going to act. What's that force going to be? It's a lot of math to do in your head, right? 100 grams is how many kilograms? 0.1 kilograms, that's right. Oops. So then you got to multiply that by what? G? So 1? All right, this one I hope doesn't stress you out too much. Sine of what angle? 90, that's right. The rest of this is usually 1/3. This has to be the mass, though. It's not the weight. So this is going to be 0.1, 1/3 ml squared. And then this is 1 squared. Now the rest is math. You guys can do math. I'm not worried about your math. This is how you figure out what alpha is. You'll get a number. It's important that you understand what that number is, like the units. So this side, remember, is meter newtons. And this side is kilogram meter squared. So when you do all that division, the only thing left are the seconds part. This will be radians per second squared. I don't know what the answer is. My gut tells me 15. Is it 15? I think it's 15. My gut tells me 15. It has to be 15. If my gut says it's 15, I've never been wrong. Actually, I was wrong twice this morning already. Radians per second squared. Now, this part, hard for you to hear. This acceleration only exists for an instant. An instant. And I need you to understand why, because if I was writing a test, this is exactly what I'd try and see if you guys could do. If you could really interpret what's happening here. After it rotates for a second, it'll be like that, right? Do you understand that the acceleration's going to change now? The force is still straight down, and the torque arm length is still the same, and the moment of inertia hasn't changed. What has changed? Yeah, the angle has changed. The angle's getting smaller on one side or bigger on the other. It doesn't matter which one it is. 90 is optimum, so anything that's not 90 is going to make it smaller, which means the acceleration's changing the whole time. So this is the answer, but it's only the answer when it's horizontal. The moment it starts to move, it starts to change. All right? I want to talk about something that's both at once easier and harder than this, but I want to make sure that there's no questions about this one. Feel okay with this one? This is pretty numeric. All right. Here's the one I want to talk about. This one's going to be, I don't know if you're going to find it easier or harder, but it's the question about the kid and the fire escape. Did you guys read that question in the homework? Where the kid's going to jump out of his window of his bedroom and he's going to hold the handle that's going to help him down? Obviously, you didn't get to that one. That's okay. We're going to get to that now, all right? I want to go back to the days when we dealt with Atwood machines. I know that fills you with happiness and glee because they were so much fun to work with. So to deal with an Atwood machine this time, I'm going to have a pulley like that, okay? But this pulley, do you remember first semester how the pulleys were all massless pulleys? Those days are gone. This pulley has a mass M and a radius R. I'm going to hang a weight off of it. That's a hideous weight. Let's do better. Do better, Mr. Shelton. Do better. I'm going to hang a weight off of it. And let's say that this weight has a mass of 2m. Okay, we did this problem in class already. Do you remember the thing that was spinny in class? And we hung a weight off of it and made it spin? It's the same thing. It's just that the spinny part of this is sideways. Okay? So my first question for you is, when we did the spinny thing in class, did the weight just fall to the floor, or did it drop slowly because we had to wait for this to start spinning? So we note that, and this is what you should put in your notes. In this system, when the pulley has mass, it has inertia. That means it's going to resist this acceleration. It's not going to want to just spin out and have the mass hit the ground. It's going to slow the mass down, make it harder for the mass to fall. Most importantly, and this is the big words I need you to know, it's going to create tension upwards in the string, which is going to slow the weight from falling to the floor. The weight's still going to experience gravity downwards. That's not going to change. And the downward force is 2 mg. But what happens to the weight is that it is slowed by the action of the pulley. The pulley has inertia. So this is another form of an Atwood machine, one that we haven't seen before, but I think one that we can probably work out. It's not so terrible. We've done this kind of work before, and right now, if I make downwards positive for this, I think most of you remember that this would be 2mg minus what? Minus what? Can I get more of you?
Tension.
Thank you. Equals 2ma. Now, what's going to happen to the pulley? So just going to sit there or what? What will it begin to do? Would you all agree it's going to begin to rotate? So it's going to experience a torque that's going to cause it to rotate. Now, this part I would not expect you to just be able to do on your own. I expect you to have questions about it. So let's consider the torque part of this. Just like what we've been talking about, there's Newton's second law. The pulley is going to experience an unbalanced torque, and that torque is going to cause the pulley to accelerate. We don't know how much it's going to accelerate. That's what we're here to work out. So, would we all be able to agree that there are two forces acting on the pulley? I think a lot of you know where one of them is, but maybe not everybody knows where two of them are. How many of you think the string is a force on the pulley? Okay, that's not enough. So let me tell you, the string is a force on the pulley. It pulls downwards on the pulley. That's one of the forces, and it has to be the same tension as is on the mass. Anybody want to hazard a guess where the other force is on the pulley? James, you hazard a guess early. I want somebody else to hazard a guess, or I'm just going to pick somebody. Yes, ma'am?
Isn't it like the center of gravity on the pulley?
Yeah, the thing that's holding the pulley in place. It must be pulling upwards on the pulley to keep the pulley from falling. Now, the truth is, there's another force acting on the pulley. One I didn't think about when I made my number 2. When I said number 2, not made my number 2, when I said number 2. When I said there were two forces, there's actually a third. Can somebody think of what the third force is? Yep.
Normal force?
I would probably call this one the normal force that's acting on the pulley to keep it from falling. But what's making the pulley also want to fall besides this force? Yes, sir?
Is it the weight of the
Yeah. Well, it's the weight of the pulley. Yeah, the pulley's got weight. So the pulley's got mg downwards. So the pulley has three forces acting on it. It's got its own weight being pulled downwards by gravity. It's got something that's holding it from falling. Well, I'll say it's a normal force. But then there's also the tension on the edge of the pulley. So three forces act on the pulley. But the pulley doesn't go anywhere. Right? The pulley just stays where it is. But it does spin, right? So the difference here is that the net force on the pulley is 0 because it doesn't go anywhere. That's important. The pulley doesn't change location, so the net force has to be 0. We do know it spins. And here's where you really have to be looking for the hard stuff. Only one of these forces causes a torque. And it has to be the one that doesn't act at the pivot point. Do you all recognize that the pivot has to be at the center? Because that's where it's mounted. That means that the normal force and the weight don't cause a torque. But the tension from the string does. So, torque. We know it's got 3 parts. Those are my 3 parts here. This is the sine part. But this will be R, the force, and then the sine of the angle. R represents the torque arm. That's pretty easy. Radius of the pulley. Force applied to the pulley. Think that's pretty easy too, don't you? Tension in the string. This one is not as obvious as you might think. the angle for any pulley has to be 90 degrees. If you try to pull the string at any other angle, it will just wrap up until it comes off at 90 degrees. So it doesn't matter what direction you pull on a pulley, the angle always comes off, the string always comes off the pulley at 90 degrees. So for all pulleys, this is always 90. Like I said, if you try a different angle, the string just unwraps some. It's not a big deal. So we're left with RT equals I alpha. So in your notes, make sure you realize you still have to apply the rules for how a torque is applied to the pulley. You could have more than one string on a pulley. We have already done that a couple times this year. We've hung a weight on both sides of a pulley before, and we've had a table where there's a weight on the table and a weight hanging off the table, and there's a pulley in the middle. In all of those examples, the pulley had no mass, but when the pulley has mass, it's going to change things. Now this part, I think, is the hardest part, and I would write yourself a few things. We need to find a way to make this and this have common variables. That's our next goal. It's the hardest part about this, is remembering to find a way to bring these two things together. I don't think it's a big stretch to consider the pulley to be a disk. Is that okay with all of you? A disk has a moment of inertia of 1/2 mr squared. This is why memorizing those moments of inertia will make it faster. Otherwise, you have to look it up in the table I gave you, or look it up in the book, or ask Google something. Because the pulley doesn't have to be a disk. They can make it a ring or a ball, or who knows. They can do whatever they want. They're the test writers, and they're mean like that. But I think for this exercise, this part is pretty easy. You substitute in the moment of inertia. It's alpha that's the issue. This is where every student has trouble. And I want to remind you, the pulley can't turn without the box moving, right? Would you all agree that how much the box moves has to do with how much the pulley turns? Can we all agree with that? If that's true, then all of these things come back from a couple weeks ago. Do you remember these? So there's one for displacement, which would be how far the box goes. There's ones for velocity, which would be how fast the box goes. And then, of course, there's one for acceleration, which is how fast the box accelerates. We now have a connection between how fast the box accelerates and how fast the pulley rotates. This is our connection. This connects the rotational part of our problem with the linear part of our problem. So I'm going to put all of it in terms of the linear part, because it's easier to watch the box fall than it is to measure the pulley spin, right? A motion detector, you see a lab in this, right? A motion detector can measure how fast the box falls. That's easy. So I'm going to make a substitution, and I think you'll agree with it, that we could write this thing as RT equals 1/2 mr squared times A over R. I put everything in terms of the radius of the pulley. Now, I know you're looking at that and thinking, man, that just looks like gobbledygook, lots of letters. Doesn't it? I'm doing this on purpose, though. This is the hardest example we will ever see for this stuff. What you're looking at right now is as hard as it will get, ever. But it's kind of hard. There's a lot of crap here. I don't want to minimize it. But something happens every single time that makes this become much easier. if you're really paying attention to the letters. First, do you notice that there's an R here, which will cancel with one of the R's there? And do you also notice there's an R on both sides of the equation, which will take out the rest of the R's? We tend to think that the radius actually has something to do with the problem, but what we find out is that because the radius is in both the moment of inertia and the acceleration, it always cancels out. The radius determines how much torque there is. The radius determines how much inertia there is, and therefore the radius determines how much acceleration there is. You put it all together, and you get something that doesn't have the radius in it at all. This will happen almost every single time for one of these problems if you decide to put it all in terms of the linear acceleration. I promise. I know that this was a lot. There was a lot to deal with. I told you it wasn't going to be easy. We're going to do this tomorrow for a little bit in the beginning and do some practice. A bunch of practice. It'll be less difficult after tomorrow.